The mean value theorem of integration. Notice that I added the word of integration. There is, I don't know if you noticed by now, there is a parallel between integration and differentiation. And we have rules that apply to in differentiation and similar rules or corresponding rules that apply to integration. For example, we have the power rule of differentiation, right? And we have the power rule of integration. We have the chain rule in differentiation, and what did we do when we did integration? Well, we did substitution. We have the mean value theorem, MVT, in differentiation that tells you that a function that is continuous between n and b, there is a point C where the slope of the derivative of this function at x equals c will be equal to the slope of the secant between a and b. Remember, that was the mean value theorem of differentiation. And parallel to that, we have mean value theorem of integration. So what does it say? It says that suppose f is continuous on some closed interval from a to b, right? Then there exists a number c and c is less than or equal greater than or equal a and less than or equal b. So c is a number inside this closed interval a, b, such that the f of c, that particular c, equals the average value of the function, which of course we see from the top will be 1 over b minus a, the integral from a to b of f of x dx. So very similar in nature to what we had in calculus 1. One thing to note is that if you think about this particular problem, you can see that it's a combination of the mean value theorem plus FTC. So notice that the above incorporate mean value theorem and FTC, fundamental theorem of calculus. Okay, this is something that food for thought. But that's it. That's the theorem itself. And what come now is I'll give you an example or two as long as time is available. So here comes the mean value theorem example. It goes like this. That will be the second example, I believe. I gave you one earlier. Let's use the same function, f of x equals 1 plus x squared, on the same interval, closed interval -1 to 2. Okay? We want to find c such that the integral, let's write it here, the integral from -1 to 2 of 1 plus x squared dx equals f of c times 2 minus -1, like so. Okay? Actually, this is written a little bit awkward. I just copied, but on second thought, I would have write it as the following. need to find C such that f of C, if I'll divide both sides by the quantity in the brackets, it will be f of C will be 1 over 2 minus negative 1 times the integral from negative 1 to 2 of 1 plus x squared dx. And this, of course, we found that it's, if by definition it's the average, so it's equals 2. Okay, and we found this in the previous example. So let's write here, recall the previous example. Where we found out the f bar I don't know why am I rewriting it, really. This is a side note right there, just in case you don't remember what happened 5 minutes ago. Anyway, so what do we do now? We're going to say that we are looking for f of c that equals, by the mean value theorem, we are looking for f of c that equals to 2, right? So by the mean value theorem, we have f of c equals f bar, right? There is a c, exists a c such that f of c equals f bar. Now f of c will be 1 plus c squared, and it's equal to, so from here you get c squared equals 1, and from here you get c equals plus or minus 1. Okay, so you have two values like that. Now, how is it possible to have two values like this, or one, if we graph this function, this will become clear. Okay, 1 plus x squared is, if this is x and this is y, has a y-intercept at 1, and it's the parabola. So we are looking at this parabola right there. Okay. Okay, we go from negative 1 to positive 2 up to here. Okay, so the integral from negative 1 to positive 2 is this area. And what we found out that there is an average value that it's c, x equal 1 or negative 1. So f of c is this value. This is f bar equal f of c equals 2. And you can see that you have two values, c equals negative 1 and c equals positive 1. And that's the interpretation of the result. Okay. I think that's it for today. Time's up anyway. So I'll open the assignment for the last two sections this afternoon, 6.4 and 6.5.